I've laid the stage. Now you're looking for those like pivotal points.
Yeah, I'm just kind of interested. Like, what are the improvements that you saw in computing from 2010 until now?
Okay.
So what are those major improvements? Okay. And then I'm also very interested once we take a step back and look at all those, looking at like what was kind of the defining moment of the 2010s that you feel like this is where things really took off.
Okay. Yeah, I'm going to hit that moment actually fairly soon in the 2010s.
Yeah.
Let me just kind of. Okay, my focus here is on Nvidia and then GPU acceleration, because this was a game changer. This changed the world.
Right.
There's no question. And I'll give you we already talked about one pivotal point, was the development of CUDA and the establishment of the ecosystem.
Right.
That was that was huge. That was the end of the 2000s. That laid the stage. Now, just over the decade, okay, it wasn't all about Nvidia. Intel did some really brilliant, great stuff too. They made real big strides in computing. They gave us the AVX vector unit. On vector units were something that you had on like mainframes and custom supercomputers and stuff. But now we had a vector unit on the CPU attached to cores in the CPU. It's like, okay, that was significant. The matrix vector operations is what scientific computing is all about.
Right.
And so that, like, boom, big performance increase. And then they progressed. They went to another layer, a better vector unit. That you had AVX, and then you had AVX 256, which AVX 2, and that doubled that performance, from the AVX.
So this was essentially increasing productivity on workstations for this kind of work.
Yeah, and clusters and just CPUs in general.
Sure.
And it was these vector units. You went from the number, from executing maybe really joyously executing maybe 4 operations per clock cycle on the CPU, to being able to execute 8 operations.
Right.
Multiplies and adds.
Right.
Fundamental stuff per clock tick. And then that doubled again, so that's like 16 times. So it's like 16 times faster than what the old days were.
Right.
And so the advent of the vector unit is one of the things that really helped a lot with scientific computing. That was, and that stuff happened during the 2010s for Intel. So they were rolling for a while. The AVX 512 was a biggie. They had some interesting stuff that turned out to be kind of flops. Like, I'll tell this little story. This is related to why I'm here at Puget.
Sure.
I'll talk about Intel for a little bit. So Intel did some brilliant stuff. Okay, there's no question. They raised the bar. They moved things forward. They increased core count amazingly, and improved the processors. But they kind of stagnated. After about the mid 2010s, they started to kind of stagnate. They couldn't deal with power problems. They couldn't get die shrinks to where they can get more power efficiency,
right,
and get the kind of performance gains that they wanted. But one thing that did come up in the 2010s was the Intel, the Xeon Phi.
Xeon Phi.
Which I want to call Phi because I'm a mathematician.
Well, that's essentially what brought you here, right?
That's what brought me here. We had moved out to Seattle, and I'm kind of hanging out. I was doing consulting work for GPU computing. That's what I was doing. I was doing workstations and stuff like this with GPUs at a time where it was not mainstream really yet. And but it was like, wow, okay, I really want to play with this Xeon Phi thing. This looks really cool. And it did look it was awesome. It was an incredible device. And so I walked in I sent mail to John, and it's like, hey,
hey, I want to play around with this thing. Can I get a job? Is that what it was?
I'd like to come down and talk to you guys about doing Because, I looked around, it's like, okay, yeah, I knew Puget from ages ago. I hate to say it, but I knew about him because...
Please tell me it wasn't
it was the oil fish tank.
It's like you who must not be named.
Yeah, everyone doing computing knew about that.
Sure.
That was so amazing. But, so I came in and said, are you guys interested in doing, you could tell, I could tell that Puget Systems was making a transition from boutique gaming into more serious computing stuff,
right.
And it was like, okay, let me go talk to these guys and see if they want to, capitalize more on the scientific computing, kind of move more in that direction, and frankly, I wanted to play with the Xeon Phi, so it was like,
it's a win-win, yeah.
So I came down and it's like, yeah, great, cool, and so I did. So and that was really fun. That started my relationship here.
Yeah.
And
it's been all downhill from there, right?
Oh, I tell you. but the Phi was brilliant, but it fizzled out. By the end of the decade, it's gone. It's gone. And it started as an effort by Intel to do a discrete GPU. That's where it came from. So it's 10 years later, and now they're actually doing the GPU that they wanted to do way long 10 years ago.
Yeah.
So that's but anyway, so that was one of Intel's kind of disappointing moments. But
what was the fate of the Xeon Phi there? So it died off. Was that due to it was built for a use case that doesn't exist, or
no? It was another one of those things where I didn't go to a specific meeting or workshop where kind of everybody decided this, like the earlier one at NCSA.
Sure.
But it was basically everybody tried it. Everybody wanted to do it because it was like, wow, this is really cool because I can actually use Intel compilers. And I have to be careful about vectorization and parallelization, but I can optimize the code so that it actually runs really well on here, and there's serious performance to be gained. But the bottom line was that, in spite being touted as being easier to do, it was actually not easier to do. Easier to do than GPU computing.
Right.
Easier to work with than CUDA. And at the end of the day,
that's where that moat that NVIDIA had kind of built, CUDA, that's where that was so important.
Yes, that's where it was so important. The developer ecosystem was just brilliant, and it turned out that it was not easy to program for GPUs, but it was not anywhere near as easy as everybody thought it was going to be to program for the Phi. And by the time you put the effort in, it was essentially the same amount of effort, and the GPUs were faster. And Intel canceled.
With that.
They canceled a supercomputer that was going to be. I mean, it was a big a big DOE contract got scrapped. It was like that was the end of it, and that was the end of the Phi. It was gone.
Wow.
So that was not good for Intel. But,
sure.
But Intel started off really great. They did some just brilliant stuff. Towards the end of the decade, they were, a lot of questionable things going on at Intel. Just really not so great. I think things have turned around for them now. They have a new CEO. Things are looking good. They've got some pretty good ideas coming up, and they're making acquisitions that are really intriguing. That'll get to my predictions later.
Sure. We're looking forward. Yeah.
But anyway, so that was Intel. Then there was AMD, and like I said, unfortunately and really sadly, Intel they just edged into the boom on cluster computing, the supercomputing boom and AMD did nothing. They just stagnated. The Opteron they didn't advance it. The best thing that AMD did during the decade was Lisa Su, their CEO.
Sure.
She's brilliant. She's the real deal. She's an engineer. She's great. And she's turned that, as far as I'm concerned, I give her most of the credit for AMD's resurgence.
Wow.
And they're back stronger than ever. they're innovating. They're doing new stuff
Yeah.
that everybody's going to be following. Okay, so they are back, but they were missing. They were gone. They were missing in action during the 2010s. But there was other cool stuff that was going on. There was things that looked like they might explode, like they just might. IBM had the power architecture is just brilliant, and there was like this open power. It was like, oh my goodness, they're gonna. That's one of the best CPU architectures ever, and but it's proprietary. It's IBM stuff. It's like, oh, now there's open power. Like, whoa, okay, so maybe this is going to take off.
This was back right in the middle of the decade, right? This was like
is in the
2014,
middle of the
2015
decade.
time.
Yeah, this is a few years back, and so that looked hugely promising. It looked like Nvidia was going to. And Nvidia
It was
did.
at
dive in with-
GTC, wasn't it?
Yeah,
It was at GTC
Yeah,
that they were launching
Open
that, yeah.
Power Conference was happening simultaneous with GTC.
Right.
So that looked really promising. I was going, oh man, because they were IBM was licensing design. It's like, oh man, if somebody can make these CPUs, this is something that's really competitive. And it looked like Nvidia was going to go, okay, we're going to like really do our own.
I thought that's exactly where they were going.
Yeah, a lot of people did. I sure did. But they backed down. So that kind of didn't happen.
Do you have any insight, any thoughts into kind of why that happened?
I know why it happened. The reason that happened is that the x86 architecture is so ingrained.
Oh, sure.
And actually, this was at GTC. Oh man, was it even last year or year before? But I was listening to Jensen's keynote, and there was another. I'll come back to that Jensen keynote. Okay, remind me if I get lost. But so there was that. There was alternative architectures. Okay, it was looking like the 2010s were going to be a decade of towards the end of alternative architectures, maybe something really interesting. The other architecture that looked really strong towards the end was ARM, and it's like, whoa, because they started making ARM process. ARM's licensed. Anybody can build ARM. It's licensed, so you have to pay.
Sure.
But the core design is really good. It's a RISC processor. It's like it's in a sense like cuts a lot of the old Unix stuff back in the day. Everybody had their own processors, and that architecture has some real strengths, and it's possible to do really high performance stuff with that. And you had high performance ARM. It's like, wow, and and it's still going. But again, NVIDIA was so well established, and it looked like NVIDIA might go with ARM, and they have to some extent. They still do a lot of stuff with ARM. You have Tegra, and that's their own ARM processor, and but it looked like they might do something on the high end with ARM. The real serious high performance computing with
Sure.
ARM, and it's possible to do that. But it's okay. Now back to that keynote with Jensen. You had open power and you had ARM, and the kind of the key player here was NVIDIA, because accelerators were so well established at that point. It was like, and NVIDIA, Jensen he was talking, and he made a comment, and it was like, he was talking about platform stability and all this, and then he said something like x86. And you could just hear this tone. I picked up on it immedately, because I was like, in a way, I could hear in his voice that he was just kind of going, crud.
Yeah. There was defeat in the voice.
There was a little bit of defeat there.
Yeah.
It was practicality. It was, Jensen Huang is a brilliant CEO. He's
Sure.
fantastic.
Absolutely.
And so it was like, okay, it's the best way forward is for us to keep with Intel, as the underlying architecture and just kind of go with that.
Right.
And so those things they had promise, they sparked, and they may still resurge. That I think alternative architectures are just prime, but so that kind of took care of all the other players. So nobody really came out shining at the end of the 2010s other than Nvidia. Intel, like I said, Intel did some really brilliant stuff, especially in the first part of the decade.
Yeah.
It was great.
And as exciting as AMD is right now, there's still a lot to prove, essentially.
Yeah, and they missed the 2010s.
Exactly, yeah.
So, but, okay.
So I do want to, I think I know where you're going. I would love to talk a little bit about, like, what was, of all these things that happened in the 2010s, like, what was to you, the defining moment where, like, things just kind of clicked and things accelerated rapidly?
The thing, okay, I think there's a moment. I think lots of people will agree with me that it was 2012. It was 2012. Okay, and that's okay on NVIDIA hardware. This was at the time of the Fermi architecture. This was kind of like the base. This was the Tesla C 2070. This was this stuff was really good. The GeForce, you had the GTX 580, 470, those gaming GPUs, which were just amazing. They were great. And the CUDA had advanced really a lot. That was the Fermi architecture. It was 2012. Geoffrey Hinton, kind of one of the most persistent machine learning, deep learning, neural network researchers. He struggled through the AI winter, trying to promote the use of neural networks for AI.
Okay.
For machine learning with neural networks, and that's a whole other story right there. Okay, that's actually one really interesting. But it was a shame that he kind of got pushed aside by some of the big names in AI with the traditional approach to AI, saying that neural networks were no good, that they were not going to happen, and it just derailed everything for it over a decade. It was really sad. But Hinton persisted. I mean, really persistent. Okay, and the Godfather. He's the Godfather. The people that really brought all of the modern machine learning stuff to light came from most of them came out of Hinton's group.
Okay,
and in 2012, okay, there's this competition that had been going on, and this is it's called the Large Scale Visual Recognition Challenge, and this was with ImageNet, and this was a big collection of images, and the challenge was to classify them, to be able to recognize objects in images.
Sure.
And this had been going on, and people were doing, traditional machine vision stuff. Computer vision has been around for quite a while. It predates, what we're looking at now with machine learning stuff, the neural network stuff.
Right.
And but this was a biggie, and in 2012, Alex Kershevsky presented a paper, and they competed in there, and they blew the competition out of the water. Massive improvement on the error rate, and they did it with a convolutional neural network, AlexNet. Okay.
Okay.
That that in itself was a game changer, because this was like, wow, that worked. It was, everybody took notice of this. This was like hugely important. But the thing that
what was more exciting? Was it the performance gain, or being able to see what it is that you could actually do with it?
Well, both.
Both, yeah.
Yeah, but the performance gain, okay, what kind of made this possible? The thing that really cemented it, and to me it's a pivotal point. They trained AlexNet on a workstation with two 580 GPUs in it. GTX 580s
right.
in there. Boom. That was the game changer. That was the game changer right there. Because everything before that was on massive CPU clusters. You know, the huge problems. And here is this kind of this convolutional neural, this new idea. It wasn't really a new idea. This stuff goes way back. I played around with neural networks when I was a grad student in the 90s.
Wow.
Yeah, this stuff has been around that long, but it didn't take off then, because we didn't have the computational power to
Sure.
really exploit it, and there wasn't the huge amounts of data and stuff that we have now.
So that's a good point too. Yeah.
But in 2012, everything kind of came together. The GPUs were good. CUDA was in place. Hinton persisted, and everybody did brilliant work, and the fact that they were able to do this on a workstation with a couple GPUs, you know, they coded that stuff up for CUDA.
Yeah.
And it was amazing that from that point on, GPU computing exploded. That was the start of the machine learning. I don't know what to use other than explosion
Sure.
that we've had for the last several years. And that completely transformed NVIDIA. Because if you look at what NVIDIA's done since then, I mean, everybody wanted to compute on GPUs. And you know, more towards the end of the decade, you started getting these frameworks like TensorFlow and, you know, all that stuff, PyTorch, all these great things going on there, that were designed really kind of in a way to exploit the architecture on a GPU really, really well.
Right.
These tensor operations are great on GPU. And that was perfect for these neural networks, especially the convolution networks. So it was a perfect fit. The performance was outstanding, and everybody could do it. You could buy a gaming GPU. Okay, that was Fermi. That was the 580. You had things really kind of came forward with the 680 and the 700 series, the 600s on the G4 side. But you had the Tesla, like the K10, K20, K40. Those GPUs that came up after this stuff started, with the machine learning started exploding, and the K40. Those GPUs, those Tesla GPUs, wound up going into supercomputers. They wound up getting deployed into big clusters, and because they had so much performance, the ecosystem had developed so far that, I mean, yeah, that was a huge leap in computational capability.
Sure.
And it only got better.
Yeah, I can't help but think back to, I remember attending GTC back in, oh man, I can't even remember what year it was at this point, maybe 2014?
Yeah.
Whatever year it was that they launched the Titan.
Yeah, yeah.
And there was something about that event and them launching the Titan. They just felt like that changed the game for everyone.
That was pivotal. That was actually where it was like really in your face how much things changed.
Yeah.
Because it went from over the course of a year. You know, the 2012 the ImageNet, the challenge there, that was like the wake up call. Everybody was like, this is what we got to do. Then they spent a year doing it, and then, you know, everybody started working on it. NVIDIA's doing more and more and more work to support this community, And then, yeah, that GTC, I remember it. It was just palatable.
Yeah.
It was so much excitement. And, and the Titan was freaking great. Right. You know, I mean, yeah, the Titans have just been wonderful. And they've just gotten, like, they've doubled every time. There's insane performance out of those cards. But yeah, you could just feel it. Jensen was up there on stage with that Titan. It was just like...
Oh, you could tell he was holding his baby.
He was like, this is killer. And it was. And it was not a cheap card, but it was like, anybody really could do that.
Yeah.
And, and those GPUs are just brilliant. Everything since that time, you know, back in the early days, GPUs were, when you pushed them for compute, yeah, sometimes they would fail. You know, they were not really, they were made for gaming and stuff like that, and it was just like, but NVIDIA just nailed it. They improved the architecture so much, it became so reliable. By the time you got into the Pascal architecture, that's where you've got like the 1080 Ti.
Yep, yeah.
That's the biggest workhorse for machine learning. I mean, that's like the default standard for somebody doing development work and doing even production work in a workstation environment and stuff like that. That defined it. They were so good and were very, very reliable. Heavy load constant. Great stuff. And then on the Tesla side, along with that, you know, the P100, P40, whatever.
Yeah.
Fantastic. But yeah, that just exploded. The whole AI thing, the frameworks with the GPU acceleration, it's incredible how from AlexNet to some of the modern stuff that's being done in research, like at Microsoft and Google and stuff like that. Huge, insanely huge amount of billions of parameters to optimize. Just crazy. NVIDIA's just keeps rolling. You know, they to me the Volta, which we didn't really get Volta in the GeForce other than the Titan V.
Sure.
But that one really changed things for supercomputing. The V100 has like crazy double precision floating point performance, really, really good. So it quelled all those issues about like, well, yeah, we need double precision for our scientific work. It's like, here you go. So
now that's not as important on the machine learning side.
For machine learning side, no. And in fact, that was the next thing they did. You know, you've got these tensor cores. They went the other direction.
Right.
It's like, wow, okay, we can get a whole lot more performance if we drop the precision. It's like these models are huge and they're statistical. It's like, all we have, you know, there's so many parameters involved that as long as the model itself doesn't numerically blow up, then you can get away with a lot lower precision. And they were great. And so now you've got tensor cores and things related to that are just, again, double the performance.
Right.
So that's just crazy. And then you know, kind of in a way from the HPC angle and stuff like that, kind of a crowning moment, if you will, to end the decade. Mm-hmm. You've got the Oak Ridge. You got the DOE machine at Oak Ridge National Labs, the Oak Ridge Summit. That is the fastest supercomputer. That's the fastest computer in the world right now.
Wow.
That's number one on the top 500 list. That is like 200 petaflops, which is like, if you don't know what that is, it's like just a whole lot.
Yeah.
Okay, it's like crazy a lot. You know, they're trying to add another zero onto the numbers there, but and you know, that all kind of came into place. The supercomputer there before that was on Opterons and Nvidia GPUs.
Okay,
that's what Summit replaced, was that old machine. Which was great. It was the fastest computer in the U.S. The Oak Ridge Summit, that's on IBM. That's on Power Architecture. That's Power 9. But that 200 petaflops, 90% of that comes from NVIDIA GPUs.
Oh, wow.
Yeah. Those are V100s in there. Okay, I looked at some stats on that. There's 4,600 nodes. So that 4,600 units, that's Power 9 in there, and each one has 6 Tesla V100s in it. And and the GPUs are what really, I mean, that's a great architecture. There's a lot of kind of unique things about that architecture. It's the fastest supercomputer in the world. Okay, you hope there's some unique things about it, right?
Yeah.
But what's driving it is the NVIDIA GPUs. They're just great. So that ends the decade with NVIDIA, and it was just crazy. The performance gains from the beginning of the 2010s to the end of the 2010s on GPU computing, and the uses, the amount of it. Anybody can do this machine learning stuff. Anybody can do this. You get a workstation with a modern gaming. You can take your gaming rig. You can buy what is essentially a gaming rig, and expand it a little bit. Put a couple extra GPUs.
Sure.
Right. Now you have a research workstation for doing great machine learning work, and everybody can learn how to do this. The frameworks have become so good, and the usability is increasing massively. So it just exploded. And there's no, they're talking about a little bit of a kind of a slowdown because this hasn't been in the business world. Okay, it's been hyped like crazy.
Oh,
right?
Absolutely.
It's been hyped out.
It's probably the buzzword. Yeah.
Yeah, it's just like insane what people's notions of what this stuff is. It's like, no, it's not. It's not as. It's not Terminator stuff. Whatever.
We don't want to call anyone out, right? Elon Musk. But.
Yeah. but the reality is it's just fantastic, and anybody can get involved. The tools are wonderful, and people can do this, and they are doing it, and people are doing great stuff. On the research side, this is where you need like the mathematics background, and because this is really serious stuff under the hood. But the usability for actually applying it and working with it is accessible to everyone. It's moving forward like crazy. It's
insane to think that it's only been 8 years, basically.
Oh, I know. That's the thing. So that's to me that's the most significant thing in the 2010s.
Absolutely,
is the explosion of GPU computing.
So let's wrap things up here then, and look forward a little bit. Let's think about what company, maybe it's the same one, but what company you think will be the biggest player here in the 2020s, and what you kind of hope to see in this next decade.
I thought about that a little bit.
Yeah.
And I don't know.
I think that's a fair answer.
Yeah, but I'll tell you why. First of all, I have no reason to doubt that NVIDIA will move forward in a massively big way into the 2020s. Because they've got so much momentum. They're almost unstoppable at this point. And brilliant people. They've just kept feeding into this ecosystem, and they've been hiring brilliant researchers. There's people doing serious machine learning, autonomous driving stuff.
Right.
NVIDIA's huge in this. Robotics. NVIDIA has those people on their payroll now. Researchers. They're moving the whole research bar forward. So, and they've got tricks up their sleeves. They can do things. They can optimize the architectures more specifically to support this kind of work. And I have no doubt that they will. They'll still be doing the gaming GPUs and stuff like that. That's still going to be one of the things that drives it forward. And, and keeps finances flowing to facilitate everything. But their GPU computing is self-sustaining. I mean, it's totally great at this point. So they're in a really good position to dominate again in the 2020s. But there's one kind of fallback, or one kind of downside with NVIDIA, is it's NVIDIA. Now, okay, you can,
sure.
That means a lot of things to a lot of different people.
Sure, yeah.
But the thing is, it's proprietary. It's a little bit of a closed system there.
Right.
And, not everything is open, and it's one vendor. So that some people go, whoa, okay, that makes people uneasy. And plus it makes startups and stuff really, really hungry. It's like, okay, how can we get in here?
Yep.
And there's so much work being done on alternative architectures, especially on computational devices specifically for machine learning, for this type of workload. And some of the designs look really, really, really good. And I think, NVIDIA's going to do their own thing, and they're going to keep rolling. And they've got so much momentum, such a good ecosystem. But Intel is is in a pretty good position. I don't know if they'll exploit it or not. But they have the potential to build a really good ecosystem. They're making noises that they exactly want to do that.
Right.
This what do they call it? Sorry, Intel, please forgive me. They've got some brilliant initiatives going on right now as far as actually creating ecosystem. Plus, they're working on their own GPU, and this is going to be geared towards an accelerator. And they bought Habana Labs, this Israeli startup company that has a chip design that actually looks like one of the more promising of the things. So, they bought Nirvana, they bought some stuff a few years ago, and they've kind of moved forward. They haven't really, had a big hit with that. They haven't really done too much, but they might really be able to compete with NVIDIA, and they've got tons of money. They have great resources, brilliant people working there. So they're in a pretty good position to be very disruptive. I don't know if they can do it or not.
Yeah.
But I would say, and then you've got AMD. Okay, now AMD is they're killing on the CPU side, but they don't really have much on the accelerator side. I mean, they do, and you can do the stuff on AMD GPUs, but it's not a great experience.
Right.
If anything, ironically, the work that Intel is doing may benefit AMD. Maybe more than Intel. because Intel, nobody has CUDA other than NVIDIA. Okay?
Right.
That's plus and minus there. But there's OpenCL. And OpenCL is an alternative for heterogeneous architectures.
Yeah.
And so you can compute for all kinds of devices with OpenCL, including FPGAs, field programmable gate arrays, right? Which is another kind of hot thing. So Intel essentially has to develop that ecosystem. If they do, it will benefit AMD also.
That's true. Yeah.
And it will benefit all of the alternative architectures that don't have CUDA. So it's going to wind up being a whole bunch of people against CUDA. Maybe. That's 10 years. Yeah, this might go. At this, this was another one of those things that people decided. It was like, okay, should we do OpenCL or should we do CUDA? It's like, let's try OpenCL. Oh. No.
Becomes pretty obvious pretty quick.
OpenCL is awesome, but it was not really it's not really, in my opinion, I looked at it, I just cringed. And I didn't want to mess with it. And unless it was wrapped in like brilliant libraries and frameworks and stuff like that, it's like, I don't think anybody else is either. but it could end up being wrapped in brilliant libraries and frameworks.
Right.
And Intel's in a good position to do that. If they do that, then actually that could ultimately be a very, very good thing. So that's kind of my take on where things are going to go in 2020. It's actually still pretty hard to predict, but I think we're going to see emergence of some alternative architectures, something and an alternative.
That was the last thing that I was going to ask here. Actually, is if you see the 2020s becoming kind of the decade of specialized hardware for the specific use cases.
Yeah, and specialized hardware in general. You've got edge computing. You have a whole lot of things that are kind of laying the foundation for very specialized hardware. This Internet of Things, IoT stuff, and edge computing, specialized hardware for all of that stuff. And then you have this kind of getting tied together with a cloud kind of model of resources.
Right.
There's I think it will be a decade of alternative architectures. But I also don't think, I believe that the basic core stuff that we're doing now, I totally believe it will persist, because somebody has to sit down and write the code.
Absolutely.
Somebody has to sit down and somebody has to actually do this.
Yeah.
And so things will change, but things will remain the same. That's almost guaranteed.
You can always count on that.
Yes.
Yeah. All right. Well, I think we should probably wrap things up here.
That's great, Eric.
First of all, thank you for joining me.
Yeah.
And then thank you, everyone, for listening. Feel free to contact us and provide us any feedback. Let us know if there are any topics you'd like to cover in future episodes. Thanks.